Check it.
Okay, welcome back. Today we're going to be solving logarithmic equations. But before we get into solving logarithm equations, let's talk about how our logarithm works. Now, a logarithm, when you graphed it, had an asymptote, a vertical line that you could not cross and you could not touch. Now that asymptote could be anywhere on the graph depending on the shifting, but when you had an unshifted basic logarithm, it would always be the y-axis. And you saw that your graph would start low, go through 0, 1, and then curve off like that. Now, what this means is that the domain for this logarithm is that this logarithm's x's always stay on the positive side of this red line here. This red line is called x equals 0. So the domain of a logarithm has to be that x is greater than 0, not equal to, just greater than. All right? So you cannot take the logarithm of 0 because a logarithm can never touch 0, and you cannot take the logarithm of a negative number because the negative numbers are all out here, and you can see your blue logarithm never makes it over there. So keeping that in mind, we have to solve equations and make sure that our answers don't create logarithms of 0 or logarithms of negative numbers. Okay? Now, once again, shifting changes this, but we're not going to be looking at the shifting. We're going to be looking at the logarithm itself without the shifting. So let's get started. The first thing we want to do is just practice finding the domain of a logarithm without making a graph. Now, obviously, if you have a graph, you can just look at it and see where the domain is, all right? But this logarithm here has a shift. So instead of making a graph, we can just do what we did for square root functions. Now, if you remember with square root functions, if we had a square root of, let's say, 2x minus 1, all right, and we wanted to solve, we wanted to find the domain of that square root or solve the square root equation even, we had to take what was inside the square root and set it greater than or equal to 0, like this. Greater than or equal to 0, like that. And then we'd solve by adding 1 to both sides, and then we divide both sides by 2. And our domain said that whatever we got for our answers or whatever we did with our graph had to be greater than or equal to positive 1/2. That's for a square root, because you can take the square root of 0, but you can't take the square root of any negatives. So as long as you were greater than or equal to 0, you were fine. Logarithms are very similar. With a logarithm, you have to be greater than 0, but not equal to. Once again, you're not touching 0, so you can't be equal to 0. You can only be greater than it. So what you're going to do with a logarithm is very similar to what we did with square roots. We're going to take the argument of the logarithm, just like we took the argument of the square root. We're going to take the argument of the logarithm, and we're going to set it greater than, but not equal to 0. So a very subtle difference here. For a logarithm, the domain is what you get when you take the thing inside the parentheses here and set it greater than, but not equal to, just greater than 0, like that. Okay? And once again, you're going to add 1 to both sides and get this. You're going to divide both sides by 2 and get this. So you notice the difference is that this is x is greater than 1/2 but not equal to. So any answers that you get if you solve an equation better be greater than 1/2 but not equal to 1/2 or less than 1/2. Okay, so there's the domain. We were asked to find the domain. We did that. And now find the range. Well, the range for all these logarithm functions we learned when we graph them, these go up forever and down forever, so it's always all real numbers. So you don't have to do any work for the range, you just know it's all real numbers if you know the graph. Okay, let's do one more really quickly here. Now this is a much more complicated much more complicated function rather. And it's got vertical shifts and horizontal things going on here. It's got a flip, it's got a dilation, a stretch. It's got a lot going on here, but that doesn't change the domain. The domain depends on what's in here. Okay, it's what's inside that counts. Anyway, the domain is dependent on this, right? So you're going to take that and set it greater than, but not equal to 0. So the domain is what you get when you take 3x plus 9, the argument of the logarithm, and set it greater than, but not equal to 0. So we'll subtract 9 from both sides, and we'll get this. We'll divide both sides by positive 3, right? And we get x is greater than negative 3. What this means for our graph, by the way, is that our asymptote, 1 to -3, our vertical asymptote is right here. Okay, and our graph will be somewhere like that. Okay, but we do know what the domain is now. The domain is x is greater than -3. You're going to be on this side of the red dotted line. Okay, now when you draw it doesn't have to be red, but anyway. Now what's the range? Well, the range is easy. The range is all real numbers. Because once again, your function is going to look something like that. Okay, it might be a little taller, it might be a little skinnier, it might be a little like that, or it might be really steep depending on the stretch. In this case, it's got a flip, so it's going to be upside down like that. Doesn't matter, it still goes up forever, down forever. So no matter what, if it's a logarithm, it's got a range of all real numbers. So domain and range of logarithms, done. Let's move on to the next topic. Now we're going to solve equations. Now, once again, like we said a minute ago, and just like we did with square roots, when you solve a logarithm equation, you have to plug the answer back into the logarithm to see if you're creating a problem with the domain. Okay, just like we did with square roots. So if your answer creates a logarithm that has a negative inside of it, or creates a logarithm with a 0 inside of it, then it's an invalid answer. All right, so we're going to be checking our work as we go. All right, let's take a look at this first equation here. If you look at this right here, this is a really simple unshifted logarithm. Okay, it's just a regular x here for the argument. So if you want to find the domain for this particular logarithm, you're just going to take the x that's here and set it greater than but not equal to 0, like that. And then you solve for x. Well, guess what? X is already by itself, so there's nothing to solve. There's the domain. Now keep this in mind after we get our answer, and we'll check it against this domain and make sure it's a valid answer. Now, this is a log base 36. We can't do anything with a log base anything except for 10. All right, we can do with a calculator, but this is a non-calculator section. So even if you had a base 10 log, you're still doing it by hand. So what do we do here? We can't really do a log by hand, like I said. And you can do it with a calculator if it's a base 10, but we're not doing that. So what do we have to do here? Well, we're going to change to exponential form and see if that's possible, if it's possible to solve it that way. So how do you change to exponential form? You start with that base, because remember with logarithms, that's all about that base, no trouble. And we'll take that base to the power of the thing on the other side of the equation. So it's to the power of this, and then set it equal to this. All right? And what do we get? 36 to the power of 3/2 equals x. We get this as an exponential equation. 36 to the power of 3/2 equals x. Let's flip that around because x should be on the left side of the equation. All right, so we get that. And now the question is, what is this? Well, hopefully you remember this from a previous lesson. It's called root power flip. You have a root down here, you have a power up here, and there is no flip because it's not a negative power. All right, so once again, we're not using calculators here, so this is a second root. Just to review how this works, this is a second root and a third power. And we're going to take the second root of 36, which is the square root of 36, and then take that result to the third power. Well, what is the second root of 36? Or the square root of 36 is 6. And we're going to take that to the third power, okay? And 6 times 6 times 6 is what you're getting here. All right, 6 times 6 times 6. And 6 times 6 times 6 is 216. Now, you look at 216 and you ask yourself, is this a valid answer? Well, does it violate the domain at all? No. As long as you're greater than 0, you're fine, so this looks good. Okay? In other words, if you took 216 and you put it here, you'd be taking the log, doesn't matter what the base is, you're taking the log of 216, which is not 0 and it's not negative, so it's good. So, yep. Here we go, we're done. Let's try another one. Now, for this one, we have a log on both sides of the equation. Now, if you remember with exponentials, when you had if you had a base, rather, and an exponent, and then on the other side, you had another base, which was the same base, and a different exponent. If the bases matched, you could drop the base. Well, it works the same way with logs. If you have a log on this side and a log on this side, and they both have the same base, right? So log base 2 and log base 2. As long as the logs match, meaning they're both logs and they're both the same base logs, then you can drop the logs, assuming that there's nothing else. Now, you have to make sure there's nothing else there but the log. In other words, if you have another, like an extra number out here, now you can't do that. But if it's just a log equal to a log, you can drop the logs. And that leaves you with this. Now, With a situation like this, you look at it and you go, hey, I got an x squared here. I got to solve this equation. I got an x squared, and I also have an x that's not squared. I have a quadratic x and a linear x. That means I'm going to have to do my quadratic equation tricks to solve this, like factoring or quadratic formula. Well, first we'll try factoring. So either way, factoring or quadratic formula, you have to get that 0 on the end. You remember the zero product rule? Yep, we're bringing this all back. All this sort of thing does not go away. So let's get that 0 on this side by getting rid of the 3x. Okay, now we have x squared minus 3x minus 4 equals 0. And that's a quadratic equation that hopefully looks very familiar to you and you can solve. Now, let's see, how do we solve this? Well, we're going to solve it, but how do we factor it, let's say? There's no coefficient in front of the x squared, so we can use reverse FOIL, just regular factoring. We don't have to use AC method here. So you put an x, and then you ask yourself, what are two numbers that multiply to give me -4, but add to give me +3? Well, let's try 4 and 1. 1 times 4 is 4, and 4 minus 1 is 3. And, well, for this to work, the 4 would have to be the negative, and this would have to be, 1 would have to be positive. And let's test it. -4 times 1 is -4. -4 plus 1 is -3. Yep, looks good. So we have a factor times a factor equals 0. So by the zero product rule, we get x equals +4 and x equals -1. Now, you might think that because this is a negative answer, that suddenly it doesn't work. That's not necessarily the case. This negative answer might still work. It depends on what happens when you plug it in here. So don't assume that because an answer, one of your solutions is negative, that's automatically invalid. And don't assume that because it's positive, an answer is positive, that it's automatically valid. Okay, you're going to see on the homework tonight that you're going to have positive answers that don't work, and you're going to have negative answers that do work. So you must check these. Now, you have two options here. You could do the domain for both logarithms. You could do the whole thing where you set this x squared minus 4 greater than 0. And you're also going to have to do a domain for the other logarithm as well. So 3x greater than 0. This one obviously becomes x is greater than 0 after you divide both sides by 3, right? So you get x is greater than 0. This one's a little more complicated because you're going to add 4 to both sides. And then you need to square root both sides. And when you square root x squared, you get absolute value of x. Remember that? And you square root the 4, you get 2. And then from here, we learned how to t-bar, right? This is going to be x is greater than 2 and x is less than -2, which ends up looking like this. X is greater than 2, but less than -2. All right, which on a number line, I know I'm going off into the weeds here. On a number line, x is everything greater than 2, but less than -2. So it's everything that's, everything except for this little gap in here, right? Now, you can do all this, but it's not necessary, okay? The easier way to handle this, instead of going through this whole process and finding the two domains, is just to take your answer, for this type of question at least, take your answer and plug it into the logarithm and see if you're getting the logarithm of a negative or not. So let's try 4, okay? Take your 4, plug it in for x, you get 4 squared, which is 16. Minus the 4 that's here, 16 minus 4 is +12. +12, taking the log of a positive number is fine, so this is okay. Now let's try it on this side. Plug in your 4 here, you're taking the log of 3 times 4, which is the log of 12, also fine. It doesn't matter what the base is in these, we're talking about just what do you take the log of. So these are the log base 2 of 12 in both cases, which is fine. So x equals 4 is a good answer. Just coincidentally, it happens to be the positive answer, but that's okay. All right, just don't assume. Now, what about -1? Will -1 work? Plug a -1 in here. -1 squared is +1. +1 minus 4 is -3. And that, you cannot take the logarithm of -3, so that's bad. Right away, we know that this is an invalid answer. Not because it's negative, just because it doesn't work in the logarithm. Okay, and like I said on the homework, you will see a couple of questions where negative answers work fine. Okay, now once it doesn't work in one, you don't have to check the other one, but I'll check the other one just in case. What happens if I put a -1 in there? Well, this becomes log of 3 times -1, which is -3, and once again, no, that doesn't work. So this is it. Now, the good news is that you don't have to sit there and calculate the domain for each logarithm. You can just take your answers and plug them back in here. Just understand that whatever's in here cannot be 0 and cannot be negative. So if you do get a 0 or you do get a negative like we just did with this one, that's an invalid answer and you're going to cross it out. Okay, let's try this next one here. We have a log base 3 of something equal to a log base 3 of something else. So since the logs do match and they have the same base, log base 3 and log base 3, you can drop the logs. Now you end up with x squared minus 15 equals 2x. All right, and yet it's another quadratic. So once again, with quadratics, you need to get a 0 on the right side. So let's get rid of the 2x here. And now we have x squared minus 2x minus 15 equals 0. All right, and now we hope that we can factor this. Well, there's no coefficient in front of the x squared, so we can go right to reverse FOIL. X and x, right? If you have an x squared, you can just do that. And now the question is, are there two numbers that you can multiply to get negative 15, but add to get negative 2? Looks like 5 and 3, right? 5 minus 3 is 2, and 5 times 3 is 15. So 5 and 3. The 5 would have to be negative because whatever the sign is here is the sign of the bigger of the two numbers. So let's try this out. Negative 5 times positive 3 is negative 15. Good. Negative 5 plus 3 is negative 2. Yes, that works. So we have a factor times a factor equals 0. We use a zero product rule. And this is going to give us x equals 5. And this is going to be x equals negative 3. Okay, don't you think quadratics were much more difficult back in the day? They're pretty simple now, aren't they? Okay, so we got our quadratic equation done. We have two answers here, but the question is, are these two answers valid or not? Okay, before we assume that they work in a logarithm. So rather than do the domain for each logarithm, we're not going to do that. We're just going to take the 5, plug it in here. 5 squared is 25. Minus 15 is positive 10. That's going to work. Okay, you can take the log of positive 10. That's good. Okay, how about over here? Put a 5 in here. Well, 2 times 5 is 10, so that's also positive 10. So they're both log of positive 10, and they have to match because it's an equation. But yeah, that works. So it looks like 5 is good. Okay, 5 is kosher. Now, x equals negative 3. Does that work? Let's see. Negative 3 plugged into here, negative 3 squared is positive 9. So positive 9 minus 15 equals, well, that's negative 6. So far, so bad. No good. And if you plug a negative 3 into here, 2 times negative 3 is also negative 6. And in either case, you can't take the log of negative 6. So that's going to be bad. Now, it's just a coincidence that the positive one worked and the negative one didn't work, but that's not always the case, like I've said twice already. Okay, let's just try one more and we'll call it a day. So for this one, we have the log base x of 16 equals negative 2/3. Now the weird thing here is that the base is actually an x this time, but that doesn't really matter because we're still going to do the same thing we always do, which is change this to an exponential. So log base x of whatever. So x to the power of this is going to equal this. So we get x to the power of negative 2/3 equals 16. And now as an exponential, hopefully this looks kind of familiar. We did these problems where we had a power on the x we were trying to get rid of, and we used what was called the multiplicative inverse to get rid of that power. So we have this power here. How do you get rid of this power of negative 2/3? What we did back when we learned this lesson was we took both sides to a power. Okay, let's call it a for a second here. And a was just going to be whatever power would cancel out negative 2/3. Okay? And the way you cancel out a fraction is you just multiply by its reciprocal. That's called its multiplicative inverse. So what's the reciprocal, the upside down version of 2/3? 3/2. On both sides. But wait, that's a negative 2/3 right there. So these won't cancel out completely because you'll still have the negative. So put a negative on this one as well. And now the negatives will cancel out and so will the fractions. So you're taking both sides to the power of negative 3/2. Now, what's that going to do? Well, when you take power of a power, you multiply the powers. And the negatives will cancel out, and this will become 6/6, which is just 1. So basically everything goes away, just power of 1, and we don't have to write the 1 there. But this is going to be 16 to the power of negative 3/2, and that's root power flip. Okay, and actually this time we have a root, a power, and a flip. We have all three. We have a root of 2, second root, square root. We have a third power, and we have a negative, which is your flip. So you're going to write this in the form of root power flip, as we have learned. In the past, we just take the 16, we put a second root over it, then take it to the power of 3, and then because there's a negative here, we're also going to put a net power of -1. This is your flip right here. All right. Now, last time we didn't have the -1 power, but this time we do. And then you're going to work your way from inside out. So, what's the square root of 16? It's 4. You're going to take that now to the third power, and then you're going to take it to the -1 power, which is to flip it. Let's continue over here. What's 4 to the third power? 4 times 4 times 4. 4 times 4 is 16, and 16 times 4 is 64. So I'm getting x equals rather. This is going to become 64 in here. And the only power I didn't do so far is the -1, which is the flip. And what does a -1 do? It just makes it 1 over 64. And there you go. Now there's your answer, but wait, we have to check to make sure that we're not violating the domain of the logarithm. So we have the 1 over 64 as our answer. Now, once again, the whole idea was that you're not taking the logarithm of a negative number or a 0. Well, in this case, x is the base, and the base doesn't really matter when it comes to checking the domain, right? And what matters is what you're taking the log of. We're taking the log of positive 16 here. That means there's no possibility, okay, that anything is going to go wrong, because this is not even a variable. This is fixed. This is a constant. This is positive 16, so that means the domain is all real numbers here, okay? You're fine. Any x you get is going to work. So, the domain of x, I should say. So, yeah, this is good, and we're done. See you at the next video.
Check this.